Hello! Today, let's just take a quiet moment to explore one of the most fundamental ideas in our digital world, how we talk to computers. It sounds like a simple question, but the answer? Well, it's at the very heart of everything we do with technology. So, let's really think about that for a second. You have an idea in your head, a task you want to accomplish, an instruction you want to give, and somehow a machine, a thing made of silicon and wires, it understands you and does what you want. How does that leap from a human thought to a machine action actually happen? Well, when you boil it all down, the answer is that we had to figure out how to have a conversation. That's really all programming is, finding a common language that lets us communicate what we want to a machine in a way it can actually understand. But this conversation isn't exactly simple. There's this huge gap between the way we think and the way a computer actually works. So bridging that gap is the first big idea we really need to wrap our heads around. Think about our languages. They're rich, they're messy, they're full of nuance. A computer's native language, on the other hand, what we call machine language, is incredibly basic. The very first computers had to be programmed directly with just zeros and ones. And you can imagine this was, and I'm quoting the early pioneers here, slow, tedious, and error-prone. Yeah, not exactly a great way to have a chat. So naturally, we started building bridges. Back in the 50s, assembly language gave us simple little codes, words like add or move, that stood in for long strings of numbers. It was a small step, but a really important one. The real game changer, though, was the arrival of high-level languages like Fortran. All of a sudden, programmers could write instructions that looked a lot more like everyday math and logic. The conversation was finally starting to feel a little more natural.
Okay, but this created a new puzzle, right? If we're writing in these fancy new high-level languages, how does the computer, which remember still only really gets its basic machine language, how does it understand us? We needed a translator.
And that translator is called a compiler. Its job is pretty simple in concept, but it's incredibly powerful. It is itself a computer program, and all it does is translate one language to another. It takes the program we write, the source language, and it turns it into an equivalent program in a target language that the machine can understand. It's the ultimate bridge for our conversation. This simple diagram really captures the whole idea perfectly. You've got your source program, that's the code that you write, that gets fed into the compiler. And what comes out the other side is a target program in a language the machine can actually understand and run. This one simple process is the engine running behind almost all the software we use today. Now, for any translation to work, doesn't matter if it's English to Spanish or C++ to machine code, both sides need a clear set of rules. You can't just throw words together and hope everyone understands. And this set of rules is what we call grammar and syntax. It's the shared structure, the shared agreement that makes sure a statement means the same thing to the writer and the reader, or in our world, to the programmer and the compiler. Without these rules, communication would just fall apart. A huge part of a compiler's job is just to be a really strict grammar checker. This process is called parsing or syntax analysis. Before it even thinks about translating your code, the compiler first reads through it just to make sure you followed all the rules of the language. It's kind of like proofreading a sentence before you try to figure out what it means. So let's put all these pieces together. We have a high-level language we can write in, we have a compiler to act as our translator, and we have a set of rules, a grammar that we all agree on. With those things in place, we can now see the entire journey our code takes, from our mind to the machine. The journey really just unfolds in 4 simple steps. First, you write your program. Second, the compiler checks your work, making sure you didn't break any syntax rules. Third, once it confirms everything is okay, it translates your code. And finally, fourth, the computer executes that newly translated program. And that's it. That's the entire trip from human idea to machine action. So you might be thinking, okay, that's interesting, but why does this matter? I'm probably never going to build a compiler. And that's fair. But grasping this core idea is, well, it's surprisingly powerful. And this quote from one of the classic textbooks on the subject really hits the nail on the head. The way of thinking behind compilers, breaking down a big problem, defining clear rules, creating a logical translation process, that's basically a blueprint for problem solving that you can use for almost anything in software development, and honestly beyond. When you understand how this translation works, even just on a basic level, You start to think more clearly and logically. You write better code because you have a mental model of what's happening under the hood. It's a piece of foundational knowledge that just helps you tackle any technical problem with a bit more confidence.
So in the end, it's not really just about learning to code. It's about learning the art of clear, structured communication. It's about the beautiful challenge of taking a complex, maybe even messy human idea and translating it into a simple form that can be perfectly understood. And that's a skill that matters just about everywhere.